In the last class, we have seen isolated DC-DC converter. First we have seen flyback converter. So today we are going to see about forward DC-DC converter. So this forward DC-DC converter is also an isolated DC-DC converter. What is isolated DC-DC converter? In isolated DC-DC converter, the input side and output side will be isolated by electrically or physically by means of a transformer, normally by a means of a transformer. Okay, so this forward DC-DC converter also is an isolated DC-DC converter, and it is a modified buck based converter. And in the flyback converter we have seen one major disadvantage is as the flux leakage increases. As the flux leakage increases, the flyback circuit will not be working properly. But in the case of forward DC-DC converter, the flux leakage is more also, this forward DC-DC converter will work. That is, if more leakage of flux is there in the circuit, flyback converter will not work properly. But the forward converter will work even if more leakage is there. Okay, and also in the last class we have seen for a flyback converter, the capacity is around 50 to 100 watts. Here the capacity is a little bit more, that is it is about 100 to 200 watt, but not more than that. So for a forward DC-DC converter, the capacity is around 100 to 200 watt. So this is the circuit diagram of forward DC-DC converter. Okay, and here you can see this side which resembles as buck converter. So that is why it is called as a modified buck converter. Okay, here you can see diode is here, freewheeling diode is there, inductor, capacitor and resistor. Okay, this is load. So this side it is resembling as that buck converter. That is why it is called as a modified buck based converter. Okay, so here major difference from flyback converter is that here two freewheeling diodes are there, D1 and D2. There only one diode was there, and also another difference is that the dot direction in the primary and secondary. For a flyback converter, dot we have put one this side and one in this side. That is the windings of the each transformer is of opposite direction. But in this case, the windings of the primary and secondary side of the transformer is of same direction. That is why this dotted portion is showing in same direction. Okay, this side and this side. That means the winding of the primary and secondary of the transformer is of same. Okay, but same direction. In the case of flyback converter, it is of different direction. That is why for a flyback converter, dot was here this side and the other dot was here this side. Okay, so that the primary side polarity and the secondary side polarity will be opposite. Okay, but here it will be of same polarity only. Here plus means here also plus, here minus means here also minus. Okay, so the major difference are two freewheeling diodes are present and one inductor also present here, and also the primary and secondary winding of the transformer is of same direction, whereas in flyback it is of opposite direction. Okay, so unlike in flyback converter, the switch and diode D1 is not mutually exclusive. There the polarity was different na? So whenever the switch is on, the diode will be reverse biased, and whenever the switch is off, the diode will be forward biased in case of flyback converter. But here it is not mutually exclusive, means whenever switch is on, the diode will be forward bias, and whenever switch is off means diode will be reverse bias. Okay, like that only here. So so unlike in flyback converter, the switch and diode D1 is not mutually exclusive. Okay, that is when the switch is on, the diode D1 conducts current flows through the primary and the secondary when the switch is on. Okay, current flows through secondary also when its switch is on. As this diode becomes forward bias, current will be flowing through this to inductor and load. Okay, understood. But in the case of flyback converter, the polarity was different, so switch and the diode D1 was mutually exclusive. That is, whenever switch is on, diode was reverse bias, whenever switch is off, diode was forward bias. But here in the case, switch and diode is not mutually exclusive. That means whenever switch is on, diode will be forward bias, current will be flowing across secondary also. But in case of flyback, whenever switch is on, diode was reverse bias and the current will not be flowing across the secondary. But here, whenever the switch is on, the diode is forward bias, so current will be flowing across the secondary. Okay, so that is a major difference. Major difference was this dot dot thing only. That is, windings of primary and secondary is of same direction here, but in case of flyback, it was of different direction. So here the main issue with this circuit is it will be that primary side, it will be having some residual energy which will be remaining in the core of the transformer when the switch is on. Okay, so here whenever the switch is on, the primer side it will be charging, and whenever switch is off means it will be discharging. So it will not get a discharge completely. So next time whenever switch is on, some residual energy will be there. Okay, so as the cycle passes means this residual energy will be increasing. As the result, the primary side of the transformer will become saturated, which will overcurrent this switch, so it will damage this switch. So this issue have to be avoided here. Understood? Here whenever the switch is on, the primary side it will be getting charged. Okay, so whenever switch is off means it have to be discharged, but it will not get discharged completely. So some residual energy will be left across this primary side of the transformer. So as the cycle passes, this residual energy in the primary side it will be increasing. It will be keep on increasing. As the result, this primary side it will get saturated, which will overcurrent this switch and it will damage this switch. So in order to avoid that, we are using a tertiary winding and a demagnetizing diode. Okay, so here the main issue with this circuit is that some residual energy will be remaining in the core of the transformer when the switch is on. As the number of cycle increases, the residual energy of the transformer increases, which will damage the switch. So due to this, transformer will get saturated, and after few cycles it may overcurrent the switch, which will get damaged. So to avoid this issue, a tertiary winding and a demagnetizing diode is used. Okay, so also this tertiary winding is also called as recovery winding. So it will allow the energy stored in the primary to dissipate. So this is the modified forward DC-DC converter circuit. Here you can see, apart from the initial original circuit, we are having a tertiary winding N3 here, and also a demagnetizing diode also placed here. Okay, a demagnetizing diode DM and a tertiary winding is included in the circuit to avoid that residual energy issue. Okay, so this is the modified circuit diagram of that forward DC-DC converter. Okay, so here DM diode is demagnetizing diode, and the recovery winding along with that demagnetizing diode is drawn. Okay, which is connected to this primary side. So the polarity of the transformer is indicated by dot. I have already discussed. Okay, so here primary and secondary windings are in same direction, unlike in flyback converter. We have already discussed about that. Okay, so whenever the switch is on, what will be happening here? Whenever the switch is on, the input side, that current will be passing like this. So this primary side it will be charging, and the demagnetizing diode means here that polarity will be like plus minus plus minus. So this demagnetizing diode will be reverse bias whenever the switch is on. Okay, and also as the primary and secondary is having same polarity, as the winding is of same direction, this diode D1 will be conducting whenever the switch is on. Whenever the switch is on, the diode D1 will be conducting, so that, and D2 will be reverse bias. D2 will be reverse biased, and so that the inductor LS placed here will be charging. Okay, so whenever the switch is on, diode D1 will be forward bias and the inductor will be charging. Okay, so when switch is on, current passes through both primary and secondary windings. Okay, current direction in primary shown in figure. Okay, diode D1 conducts and diode D2 and DM are D2 and DM will be reverse bias. So let V secondary be the voltage across this secondary side, and VO is the output voltage. So the inductor voltage across this inductor VLX will be equal to V secondary minus V0. Okay, V secondary we can write it as input side VI into N2 divided by N1. So V secondary will be VI into N2 by N1. Okay, that is V secondary. So this VLX we can written as LX into delta ILX, where this LX is the inductance and this delta ILX will be the increasing current. Increasing current means as the switch is on, the inductor will be charging, so it will be increasing current. LX into delta ILX, which will be equal to V secondary minus V0. V secondary minus V secondary means VI into N2 by N1 minus V0 into dt. This is for on time when the switch is on. Okay, so dt. Okay, turn on time. So the inductor gets charged during switch is on, and the current flows through both the primary and secondary of the transformer when the switch is turned on. Okay, so now when the switch is off, what will be happening here? Whenever the switch is off, here, the polarity here it will be reversed. Okay, this dot side will become negative and non-dot end will become positive. So same polarity will be inducing in the secondary side also. As a result, this diode D1 will be reverse bias. And here the inductor polarity also will be changing here, and the inductor will be charged here. So this charged inductor will be discharging when the switch is open. The charged inductor LS will be discharging, and the discharging path will be like this, so that the diode D2 is forward bias, and the charged inductor will discharge across this freewheeling diode D2 across this dot. Okay, and also here also polarity I told it is reversed. So this for this N3 tertiary winding also polarity is reversed. As the result, this DM is there na, demagnetizing diode, it will be forward bias. So the residual energy which is remaining in this primary of the transformer, it will be dissipating across primary like this, in this direction. So it will be dissipating. Okay, so that is what happening when the switch is off. When the switch is off, the transformer polarity is reversed and the diode DM and D2 starts conducting. Okay, inductor LX discharges the energy stored across the load on the path load as path is short circuited, and D2 is conducting. So this is the path where inductor discharges. In primary side, as the polarity is reversed, the diode DM starts conducting, and the recovery winding dissipate the residual energy stored in the shown part. Residual energy stored in this inductor will be discharging like this. Okay, so in the secondary side, LX into delta ILX, which we can equate to here, only output is there now. Okay, this side is disconnected as the diode D1 is reverse biased here. Okay, so it will be equal to V0 into 1 minus D into T. 1 minus D into T means the switch is open, that is why turn off time, 1 minus D into T. So LX into delta ILX is equal to V0 into 1 minus D into T. Okay, so this is equation number 2. Okay, so here this delta ILX will be decreasing current as the inductor LX will be discharging when the switch is open. Okay, so 1 minus D into T is the turn off time. So equating 1 and 2, we will be getting like this. Finally solving, we will be getting V0 by Vi, which is equal to N2 by N1 into D. V0 by Vi, which is equal to N2 by N1 into D. What is this signifying? That is the output voltage can be adjusted by appropriate design of the number of turns N2 by N1 across the primary and secondary of the transformer. Okay, and also output voltage can be dynamically adjusted by varying the duty cycle. Okay, so this output voltage is depending on the turns across primary and secondary N2 by N1 and also the duty cycle. Okay, so this is the waveforms whenever the switch is on, whenever the switch is on, the voltage across switch will be 0. Okay, the primary current will, it will be increasing, primary current it will be increasing. Okay, primary side current will be increasing as the switch is on, and also secondary side also current will be there, and that inductor Lx will be charging, so secondary side current also will be increasing. Okay, and the inductor will be charging. Okay, that is shown here. Okay, and also now second case, whenever the switch is off, when switch is off, what will be the energy, sorry, what will be the voltage across this switch? It will be Vi, input side Vi will be there, and also stored energy will be there in this primary side, it will be Vi. So Vi plus Vi, 2 Vi will be there across this switch. So 2 Vi will be there across this switch. This spike is due to the presence of inductance. Okay, so 2 Vi will be there initially, and spike is due to the presence of inductance whenever the switch is off. And also primary side, no current will be flowing because uh, the switch is off only. And also secondary side also no current will be flowing. And also the inductor side, secondary side no current will be flowing as the diode D1 is reverse biased. And also the inductor ILX will be discharging through the path D2. Okay, freewheeling diode D2 is there, through that the inductor will be discharging across the load ILX. So ILS will be decreasing. Okay, and also uh, one more thing I have to tell here, that whenever the switch is off, that the energy stored in the primary, it will be dissipating through this demagnetizing diode and the tertiary winding N3. Okay, so initially this primary side it will be charged Vi. Okay, so now that Vi have to be reduced. Okay, so that Vi will be dissipating across this Dm and N3 due to this tertiary winding and this demagnetizing diode, that the energy stored in the primer side will be dissipating. So as the all the energy stored in the primary side is dissipated, then this Dm will be reverse bias. Okay, as the all the energy stored in the primary side it is dissipated, then the Dm will be reverse bias. The voltage across the switch will be Vi, because here also initially Vi was there, but that fully it is dissipated through this demagnetization diode and this tertiary winding. So after that the remaining voltage across switch will be Vi. Correct. Okay, so that is what the mode 3 shown here. So here we can divide into mode 1, mode 2 and mode 3. Mode 1 switch is on, mode 2 and the switch is off, and the mode 3 when the switch is off and also this tertiary winding and the demagnetizing diode which dissipate all the energy stored in the primary side, then the remaining voltage across the switch will be Vi. Okay, initially 2 Vi was there, so the tertiary winding, when 2 Vi was there, the tertiary winding and the demagnetizing diode will be dissipating the energy stored across this primary side, and whenever the complete energy stored in the primary side is dissipated, that the remaining energy across switch will be, remaining voltage across the switch will be Vi. Okay, and also the inductor in the secondary side, as the diode D2 is a reverse bias, sorry, diode D2 is forward bias, it will be decreased. Okay, so that is what mode 1, mode 2, mode 3. Whenever the switch is on, the current flows across primary and secondary. Okay, whenever switch is on, current flows across primary and secondary. The voltage across the switch is 0, voltage across switch is 0. The primary current will be increasing, secondary current also will be increasing gradually, and also the inductor Ls will be charging. Okay, as the diode D1 is forward bias. Then mode 2, in the case of mode 2, D2, freewheeling diode D2 and demagnetizing diode Dm will be conducting. So when switch is off, the diode D1 will be reverse bias, D2 will be forward bias, and the inductor dissipate energy stored across load, and it will be freely wheeling through this D2 path, and dm will be forward bias. So it will start dissipating energy stored across the primary. Okay, dm is forward bias, and it will start dissipating energy which is stored across the primary through the tertiary winding. Then the voltage across the switch will be initially 2 vi, and it start decreasing as the recovery winding starts dissipating energy. Primary and secondary currents will be 0, okay, when the switch is off, and the inductor current will be decreasing as the inductor will be dissipating the energy stored across the load. And also mode 3 means dm will be reverse bias, because all the energy stored in the primary will be dissipated by that time. So only d2 will be on at that time. Okay, d2 will be forward bias at that time, remaining d1 and dm will be reverse bias. When switch is off and all energy stored in the primary is dissipated by the recovery winding and the diode, dm will become reverse bias, not of reverse bias. So current flows across the inductor through diode d2, and the current will be reducing as the inductor is discharging. So the voltage across the switch will be comes to vi as the energy stored in the primary transformer is dissipated. Okay, so these all are about that forward DC-DC converter. Hope every point is clear. If any doubt, please get to me. Okay, so thank you.